Good morning, everyone, and welcome to the technical seminar of the REHVA Brussels Summit of 2020. My name is Spiridon, and together with my colleague Jasper, we'll be the host from the REHVA office. Before we start, I would like to remind some housekeeping rules. So the seminar will be recorded. The slides and the presentations will be sent to participants after the event. All attendees are muted by default. And if you want to make any questions to the panelists, please use the Q&A section that is on the right side of your screen. Please send your message to all panelists and not private. I hope you will enjoy the seminar. I will now pass the floor over to REHVA President Frank Hovorka. Frank, the floor is yours.
Thank you very much. Thank you very much, Spiridon, and I use this opportunity to also thank all the team in REHVA office for the organization of this virtual summit. So I want to welcome all the participants in it's a new Brussels summit for the first time totally virtual due to the actual pandemic in the world. I hope that we will reach the same level of information and knowledge sharing as we usually do with this Brussels summit that according to the previous years you appreciate. So first, again, a warm welcome to all the attendees. We are very pleased to have you here listening to our summit. I also use this opportunity to warmly welcome and really give a great thanks to all the panelists that we will speak today. It's really a great honor to have panelists from different parts of the world, panelists from different industry and different research fields, and it's our honor to really have them explaining who they are now in this situation. As you know, we will start our first panel with the impact of COVID-19. And as you know, we have worked at the European level with REHVA, and I will also here clearly want to thank all the people and the researchers who work inside the REHVA COVID-19 task force among the 27 members that we have here in Europe. It's really an impressive work. We went through a lot of discussions, and research is still ongoing, and we will soon release the fourth version of the COVID guidance. And it's really important also that we could use this possibility to work with other researchers all over the world, in Asia, in America, and also in Australia. And we have the possibility also to push forward the Global Alliance for Indoor Environmental Quality, who also help us to have this vision worldwide. And I will start with our first presenter because it's a great honor to have her with us this morning in Europe with Professor Lidia Morawska. So it's really a great honor to have her because she worked very hardly to push forward the research and the knowledge among different researchers around the world, and also to help the discussion and the recognition with the World Health Organization. Professor Lidia Morawska is professor at the Queensland University of Technology in Brisbane, Australia. She's collaborating with the Center of the World Health Organization on research and training in the field of air quality and health. She is also co-director of the Australian-China Center for Air Quality Science and Management. Professor Morawska is a physicist, and she also an author of over 800 journal papers, book chapters, and referred conference paper. She has been involved in the executive level with a number of relevant national and international professional bodies, and she is a member of the Australian Academy of Science. So, Professor Morawska, again, it's a great honor to have you here this morning, and I leave you the floor for your presentation. Thank you very much.
Thank you very much, Frank, for the introduction. Let me try to share my screen. Can you see my screen all right?
Yes.
Okay.
Yes.
Yeah, all right. Good morning, colleagues in Brussels, in Europe, and everywhere else where you are listening, and good afternoon from Brisbane. Many thanks to REHVA for inviting me to give this presentation. I feel very honored. I structured the presentation around 4 points: buildings, contradicting requirements, what we knew before COVID-19, lessons from the pandemic, and future, change in thinking and actions. Building contradicting requirements. Now, what we mean by this, of this complex system which building is. What you see on the screen appearing now are images from bushfires in Australia, with which the media entertained in the quotation mark the whole world for many months at the end of last year, the beginning of next year. Well, the images are from outside, but if you read the text of these news items, the worry is about the condition of the air inside the buildings, homes, schools, and so on. During the many and numerous interviews, I was asked about the topic, what to do, how to protect people. Basically, the recommendation was close up buildings, minimize outdoor air, recirculate. And of course, this applies to any situation when outdoor air is polluted, not only during bushfires. Well, several months passed, and the same journalists are coming or started coming to me asking what to do to protect and to minimize transmission and risk because of COVID. Now, we've published a paper on this topic, and numerous authors of this are on the call today. Well, in this case, the recommendation was open up buildings, maximize outdoor air, do not recirculate. And this applies not only to COVID, but to any situation of respiratory infections. Completely contradictory recommendation. This is not the only example of such contradictions. Buildings and energy. We know very well that buildings consume between 40 and 30% of energy. This is an example from the United States. If we look at the commercial and residential, we should save energy. So what is the recommendation? Or one of them, of course, this is not the only one, tighten up buildings. Well, if we look at another problem, buildings and mold. Mold is a biological agent. We don't generate biological agents, but we often create conditions under which they can propagate, like this corner here infested with mold. And this was covered by the WHO guidelines, in which I helped to develop dampness and mold. This is what we generate. So the recommendation here, then one of them, is open up buildings. Again, this is a contradicting recommendation to the previous one about energy. I'll come back to the topic, to this topic in a minute. But now, COVID, what we knew, not what we've learned during COVID, but what we knew before COVID about respiratory infection transmission. Let me say a few words about my presentation exactly 15 years ago at the Indoor Air 2005 conference, and the title of my presentation was Droplet Fate in Indoor Environment, Can We Prevent the Spread of Infection? Well, if I didn't tell you that this was a presentation from 15 years ago, this could have been easily a presentation today. And let me share the 3 slides from this presentation. I reviewed how common are respiratory infections, giving some examples from UK, the frequency of cold in children and adults, and other diseases like rotavirus, novel-like virus, and so on. Well, we could just update the data here, but the issue is the same. Another of the three slides finishing my presentation then was economics of infection spread, which goes basically in billions of dollars. This is the example from United States. Every country has similar estimates, slightly differ, but it all goes in billions of dollars. And also there are estimates how much could be saved if, for example, influenza and common colds are controlled. So what was the conclusion about the role of building designs in infection prevention? So firstly, I said that setting the key building parameters according to the current understanding of the optimal ranges would result in lowering the potential for infection spread. Also, the question was whether this is the limit of what can practically be achieved in lowering the infection spread is not known. And I suggested the need for application of the science of infection spread towards developing quantitative guidelines guiding building design and operation. Well, this could be the ending of my presentation today. I was not the only one saying this. There were many scientists and many of the colleagues on this call as well. The problem is that the science of infection transmission wasn't really used to prepare us for COVID-19. Lessons from this pandemic. I'll say a few words about the risk and the outbreaks, how to quantify the risk. The first question, which was discussed extensively and still is it airborne, the virus? We remember the statement from the WHO in March saying definitely that it's not airborne, this is wrong. Well, interestingly, we've learned not that long ago that President Trump, in an interview with Bob Woodward, and this was in February, however, the book was published just recently, stated that it goes through the air. Well, it's always worse than touch. Clearly, his advisors already have a different suggestions than those to the WHO. But things are changing, and we were very pleased to see the announcements of the last week or 2 weeks, like, for example, this one by Dr. Maria Neira, stating in a 5-minute science brief, it's not really a brief science, science in the media, that ventilation represents a very important aspect to prevent the virus from spreading indoors. Not a controversy anymore. Another statement, this time from Dr. Anthony Fauci, a little bit earlier, saying there was some real misunderstanding about respiratory droplets and so-called aerosolized particles. The aerosol and particles physicists that have approached us now have told us that we really have got it wrong over many years. And the bottom line is that there is much more aerosol than we thought. Well, not a controversy. I would say that this was never a scientific controversy. Just the fact that I'm quoting here politicians says it's all. It's not a scientific controversy. Well, there is progress, and the progress is actually, as we speak, in the last few days, there have been more developments and new countries accepting this. US CDC have been going back and forth through this accepting, not accepting. Right now, it's made steps forward from the 5th of October. So that's what I wouldn't say learned, but that's what has been accepted, what we knew. We've learned a lot from studies of outbreaks and airborne transmission. And what we've seen that while all 3 modes of transmission occur, airborne emerges as the most significant in typical public settings. Just give 2 examples. The one studied quite extensively, several papers have been published about this, including ours, where we did, or one of the papers in which I've been involved, where we've done retrospective modeling. All this modeling is retrospective, showing that what happened there in terms of infection, 45 people were infected out of 60 during 2.5 session very well is represented with in our modeling. Very different modeling was done to estimate contributions of transmission modes and viral source during the outbreak on Diamond Princess cruise ship. Here, the researchers compared what they call short-range droplet and aerosols with long-range aerosols and fomites. What we can see here that long-range and short-range together are more significant than fomites, and in terms of viral source, aerosols are more significant. Well, each of this can be questioned because these are all retrospective studies. And studies of outbreaks can only be retrospective because they are not planned. There are no researchers to investigate them. However, the body of such studies is mounting, and it's clearly pointed out to the significance of airborne transmission. So future, what's going to happen in future? And I'll start with change in actions, mitigations of all risk, airborne infection, focus on ventilation, guidelines, and empowering individuals. I started with this contradictory requirement. This is not going to go away. What we need to do is change in actions in terms of mitigation of all air risk indoors, not one at a time, taking into account mitigation of what's generated inside, anthropogenic sources of airborne infection, prevention of ingress of outdoor pollutants like those from bushfires, controlling dampness, keeping in right thermal comfort, and doing this at the stage of building design, HVAC design, considering energy demand and building operation. This is really key that in the future we'll look at the holistic picture and we'll look at this together. I'll say a few words about just this mitigation of airborne infection and sufficient and effective ventilation. Well, I'm sure you all can tell me more about this, as I'm not an engineer, I'm a scientist. But in very short, sufficient and effective, enough of it, and everywhere like in this picture. Well, we can ask a question, can we use the existing guidelines for controlling transmission? There are guidelines, there are standards, for example, guidelines for removing CO2 exhaled by the occupants. Well, not quite, because unlike exhalation of CO2 by the occupants, infection transmission is in terms of infectious quanta, which are, I'm sure you've heard this, but just for infectious agent required to cause infection in 63% of the population. Now, while we know how much is emitted of CO2 is emitted by people in terms of emitted quanta, it's very complex. It depends on the location of the pathogen in the respiratory tract, physiology of the respiratory tract, we are all different, stage of the disease, type of the respiratory activity, breathing, speaking, coughing, and the virus. But it can be done and has been done not only just now. Several years ago, we did this simulation of ventilation and infection risk in the Prince Charles Hospital in Brisbane, in this particular place, lung ventilation laboratory. Infection risk for 15 and 45 minutes, occupancy for 3 infections, influenza, tuberculosis, rhinovirus. And what we can see and expect with the increase of outdoor air exchange rate per hour, infection risk declines and declines on a logarithmic scale, and of course varies between the different pathogens because the quanta is different. During this pandemic, we've done some studies with colleagues in Italy, where we calculated as on this diagram quanta concentration and infections risk in a pharmacy or exposure scenarios before and after lockdown. I don't want to go through the details of this quite busy slide, but what I'd like to stress that calculations like this and simulations like this, for example, allow us to, like in this case, calculate the risk if in case an infected individual enters 10 minutes into this and then the risk of a customer entering at minute 26 and remaining for 10 minutes. This can be modeled quite well, as we've shown in our following papers, where we've done retrospective and prospective modeling. Now, but in addition to this efficient ventilation, there was one issue of its effectiveness, airflow distribution, direction, and risk of infection. I'm sure that most of you would have seen this slide from this restaurant in Guangzhou and have heard many times about the problems caused by, well, not only the fact that ventilation was poor in this location, but also this was unidirectional in this particular area, and then taking the flow was going from an infected person around this part of the room. So in this case, the flow direction was a problem, in addition to the low pressure of air supply. So we should prevent this unidirectional flows, but this goes to some misconceptions and again contradicting requirements. A few days ago, I received this email from somebody in Spain, advice about the university advises to avoid cross-ventilation during any lectures. And more precisely, the recommendation is to avoid opening windows and doors during classes in order to avoid air currents. So the rationale is that currents can transport aerosols from one person to another. But the problem is that this potentially reduces ventilation, hence infection risk, which is even worse than this cross current. So these things are already happening and should be taken into account. So basically what we need guidelines for engineering control in relation to infection control. And of course, such guidelines have already been developed, and REHVA is one of the leaders in this respect, as well as ASHRAE. So recommended for control measures and provided guidelines on their implementation. However, based on what I've just said about this calculation of risk of infection, more advanced guidelines should be developed to take in this knowledge into account about infection transmission. And there are many tools being developed for this, like this airborne infection risk tool, which we've developed, and I'll come back to this at the end of the presentation. So in the last minute or so, I'd like to say about this specific aspect, empowering individuals so they understand the system and can control it. If you ask anybody, just anybody anywhere, do you know what is the temperature in your home office? Well, they would say, yes, if I want. Do you know how good is the ventilation in your home office? Well, they would hesitate. Some would say maybe, most probably not. If you ask how good is the ventilation in the cinema or restaurant, where is the airflow? Definitely not. Do you know how good is the indoor air quality? Certainly not. Several years ago, we've published this paper with several colleagues on real-time sensors for indoor air monitoring and challenges ahead in using them in urban buildings. What we concluded in this work is that, firstly, much better awareness of indoor air quality issues needs to be developed, and secondly, tools to interpret the sensor data. And unfortunately, we said neither of this exists as yet, and therefore it is argued that currently available sensors are ahead of their time. What I'm suggesting that there should be a paradigm change in using data from indoor sensors, not for the purpose of data collection or network building, like it is in relation to outdoor air, but for displaying the state of the indoor environment and doing it in a meaningful way for the user to interpret, and a parameter or its proxy so an action can be taken, like this display of CO2 and traffic lights, meaning what it needs. And for this, we don't need scientific grade instruments. We need robust instruments which tell and inform and make the public aware. So to finish future change in thinking, not only action, but thinking. We need to change in thinking how buildings are designed, how they are equipped in adequate engineering controls, how all the requirements are linked, including low energy consumption. But for this to happen, we also need to think differently and about indoor air quality, how we teach about it and train students, medical students, engineering students, all students, and very importantly, the perception that we cannot afford this. The economic cost of impacts of indoor air pollution by far exceed all the other costs. Buildings, and that's what will change. I'll finish saying that every pandemic in history transformed humanity. Will COVID-19 transport our buildings? I'm very much hoping so. This is an invitation to a webinar which will run by IVIAC on these tools which I mentioned to help us to build a better future. Thank you very much for your attention.
Thank you very much, Professor Morawska, for your presentation. It was a great inspiration to all of us, I think. We already have some questions. One of the questions is, what is, or do you know what could be the impact of the humidity rate in the transmission of COVID-19?
Well, this is a very controversial questions, and they've been studies showing that this particular virus is more stable under lower humidity conditions. Maintaining the humidity at the certain range would apparently help with it. However, it's not really accepted that generally that this is the best way to control the virus is by controlling the humidity, because controlling the humidity, as we know very well, affects everything else. So this would probably be not the first mitigation measure in controlling the virus.
Thank you very much for your answer. I also have another question. You spoke about the work you have conducted on the calculation tool with the Weiss-Riley methodology and Quanta. Do you think that it could be used on the ground with for commercial malls, shops, and so on, and how it should be tuned in order to use it properly? Do you have an idea about how we can go from the research you have conducted to let's say a ground used that could lead to something which is not leading to misunderstanding?
Well, it's already being used in many places. We are working on this with colleagues in New York, and I know that it's already used in New York, and it's used in other places. The point is that the tool can be used to calculate the risk very well, of course, to the extent we can properly assume what's the quanta for SARS-CoV-2. The question, however, probably is a bit different, namely, can we generalize? Because I can't imagine that in the future, every shop, every office will be doing their own risk calculation. There's got to be something which is more general. So what I imagine will happen in the next months or years, there will be a lot of simulations done for different types of scenarios to come up with some more general rules which can be more generally applied. So it's not that every place has to do their own calculations, but it's possible as well, and it's quite easy. And as I said, it's already being done.
Frank, if I may, there's one question. One more question.
Of course.
Yeah, there's one more question about swimming pools. Lidia, maybe you can say a little bit about swimming pools. Is it a low risk or a high risk? That's the question.
Well, I don't know that I have a very good answer to this, because it depends. It depends on the pool, whether it's indoor or open. The question whether the virus is in the water or whether it is when the swimmers are preparing to swim or are swimming. So There've been some speculations on this, but I don't think there's a general response about the swimming pools. But well, basically, I would treat this its swimming pool in question as indoor environment, and then do the calculations based on what's happening there.
Thank you very much. There is another question.
And one other question.
Yeah, please answer.
One other. You showed the CO2 monitor. Can you say, if you have like a large space, like a restaurant, what you think is a safe level in terms of CO2, or maybe a safe level in terms of air exchange rate or ventilation per person? There's a lot of talk about this. I would be interested in hearing your personal opinion about this.
Well, there are guidelines about safe level about CO2 in relation to the CO2, and on that monitor which I've shown, the concentration was already approaching 1,000, and 1,000 is where the red light starts. So a concentration, let's say background concentration in Brisbane is about 430, something like this. The fact that the CO2 concentration in a shared space is low, of course, doesn't mean that the risk of infection is completely under control. However, if CO2 concentration is high, implying that air exchange rate or the air supply per person is high, there's definitely a problem then. So this is one of the best indicators, as I said, not necessarily immediately about infection risk, but the fact that there's a problem with ventilation. And this is something which I start recommending as much as possible to provide this information to people, to users, because if people realize that ventilation is bad, well, they would start doing something. To be honest, I've been carrying a CO2 monitor very frequently with me now. And in many places which I thought would be well ventilated, to my surprise, they were not. So if even experts cannot tell whether ventilation is sufficient, of course, lay people can't either. But if people know that there's a problem, they will do something.
Okay, thank you very much.
I have another question, Lidia. You spoke about changing the design of our buildings because of the pandemic. I think it's a very important statement. What are you using sensors, giving more empowering the users, but what do you think it could mean in terms of HVAC technology in the buildings?
Well, the bottom line is that we should be able, when necessary, to close up the building complete use recirculation air, which means complete mechanical ventilation, or being able to open it up, use natural ventilation, which is in generally better, more desirable, and be able to switch from one to another dependently what's necessary. Of course, such dual systems are more expensive. There's no doubt about this. But on the other hand, having this ability will protect us from the risks. And protecting us from the risk will save us by far the costs, which are by far higher than the cost of not having such systems. I'm saying that it may sound complicated. On the other hand, we are sending rockets to Mars, and there's no choice. It's not a choice whether the rocket is overheating or not overheating. Everything has to work for the mission to be accomplished. Buildings are complex, but still not as complex as sending rockets to space. We should be able to do it, and as I said, the cost, while higher, will save us significantly more cost of not doing this.
Frank, we have maybe time for one more question.
Yeah, for sure.
There are 3 persons that asked about air cleaners and whether we should look further than just fresh air supply, but maybe also devices to clean viruses out of the air. Can you say a little bit more about your opinion about that, Lidia, please?
Well, in the paper which we've published actually together with air cleaners were also included as a technology to be used. There are many situations where it's not possible to achieve sufficient level of ventilation, and cleaning the air using air cleaners is removing the virus from the air. Of course, there are issues with this because then potentially the air cleaners contain the virus. They've got to be cleaned properly. They've got to be applied properly because the question is whether they are of sufficiently high power for the area in which they are used. But nevertheless, this is a certainly means which lowers the concentration of the virus in the air.
Okay, thank you.
Thank you very much. So I think we went through all the questions. There is a last one about humidity that says, are you aware? Oops, I lost the question, sorry. Should go back. I lost it. Low humidity. Are you aware that low humidity, let's say 30%, means for the condition needs of humans that have to increase humidity to 100%?
Well, I think this was the first question. This question is asked quite frequently about humidity. And yes, we know that the virus responds to the humidity either in positive or negative way. It's deactivated when the humidity is too high in that medium range, and it survives better when the humidity is lower. But what I thought, and I think this is also the view shared by other scientists, that controlling humidity is not the first means of controlling the virus. There are other steps to do first rather than controlling humidity, because controlling humidity has impact on everything else as well, and possibly negative impact.
Yeah, thank you very much for your answer, Professor. The last question, you mentioned the potential danger for air currents with natural ventilation with opening windows from opposite side in a room that creates air currents, and that could be maybe a potential high risk. Because we are talking a lot here in Europe and especially in France with natural ventilation. So is it a risk to have air currents inside a room?
Well, this was the question which came, and suggestion which came from Spain. The air currents are created not only by natural ventilation, opening windows or doors, but also can be generated by mechanical ventilation. This air condition in Guangzhou created such unidirectional conditions. There's been studies showing infections on planes where there was also unidirectional airflow. So in general, unidirectional airflow is not good, and particularly if the occupants are exposed to this for prolonged periods of time, let's say during lessons or during flight. So this should be avoided, but it should be done in the whole scheme of improving the ventilation efficiency and efficacy of ventilation in the room. So I wouldn't recommend, in order to prevent air currents, closing the windows like that colleague worried in Spain, because this reduces the ventilation, which worsens the situation. So we should avoid unidirectional air currents, but not by lowering ventilation.
Thank you very much, Professor Morawska. I think we run at the end of the session. I know you have obligation after this meeting. So on behalf of all REHVA board and all REHVA staff and members, I want to thank you very, very much for your presence today, this morning for us, this afternoon for you. It's really a great pleasure to have you here. And I really want to thank you very much for your presentation, and I know that you are in close contact with our task force too, and I'm impressed by the quality of work that was done the last month and level of cooperation worldwide, and you are one of the leaders for that. So really a great thank you to you, Professor Morawska, and thank you again.
Thank you very much for inviting me. I'm really very happy and very much enjoyed being part of this event.
So thanks again. So I propose to go with our second speaker today. Our second speaker is Professor Jarek Kurnitski. Jarek is a professor at Tallinn University of Technology in Estonia and also at Halton University in Finland. Jarek is the chair of the Technology and Research Committee in REHVA Federation, and he has been leading the REHVA COVID-19 task force from the beginning and preparing the HVAC guidance that we already spoke about and that you can find on the REHVA website. It's been already translated, I think, in 14 languages. Jarek is the leader of Estonian Center of Excellence in Research in Zero Energy Building, and he's internationally known for the preparation of technical definition for nearly zero energy buildings, and also with smart readiness indicator here in Europe. And he's deeply involved in the work to improve energy efficiency and indoor climate of a built environment. So, dear Jarek, it's my pleasure to give you the floor for your presentation. Thank you.
Good morning, and thank you for this introduction. So I will try to provide some overview in my presentation about HVAC research and technology development needs. So Lidia told already a lot of background about mechanisms and so, but very briefly to repeat what is important when we speak about HVAC solutions and what we really can control with these solutions. This is basically the concentration of virus-containing particles, so aerosols, in the room air. And so when we speak about general ventilation solutions, basically we cannot go closer than 1.5 meters from infected person. And when we speak with personal or targeted ventilation solutions, when we further can reduce the concentration, and we also can closer to that 1.5 meter. So main research, let's say, themes and topics, if we will try to list, indeed it's very important to be capable for the infection probability calculation. We need to know how much ventilation is needed, and there are very many questions related to air distribution. So these apply for general ventilation, personal and targeted ventilation, and I also would classify performance of air cleaners as an air distribution issue. Then also, let's say, the hygiene of ventilation components and cross-contamination issues, especially related to the recirculation, will deserve attention. So today we know about this disease that most of the cases have been either associated with close proximity or have been happening in spaces which simply have not been ventilated, or the ventilation has been very low. So from such events, very often ventilation rates 1-2 liters per second per person have been reported, and this is basically 10 times less than the ventilation should be. But we still do not know what is the ventilation rate we should have to control this infection risk. We know, for instance, what is ventilation in well-ventilated rooms. So, for instance, in meeting rooms or classrooms, if these are ventilated according to the current standards, we can achieve about 5 air changes per hour. And just compared to the recent talk by WHO, when they started to talk about 6 air changes per hour would be very good ventilation rate, what can be recommended. So only these type of rooms, let's say, which are for high occupant density, when we are close to that ventilation rate. And in most of rooms, indeed, it's something less. To calculate this infection risk, then we need to know what is emission of a virus containing aerosols, let's say quanta emission rate in more specific terms, and there are some examples for different viruses. And actually the calculation is exactly the same for all of these. So common cold is something what is with similar emission rate, about 5 quanta per hour, very often used for that. And this is similar for this SARS-CoV-2, according to the latest data we have. If we are just, let's say, resting and we do not speak or we do not have any other, let's say, aerosol generating procedure activity like singing or loudly speaking, something like that. And then we also know that for the influenza, these generation rates are somewhat lower. But this shows to make such a calculation, results will both apply in similar fashion for common cold and SARS-CoV-2. And I will show some examples. So these will be included in the latest version of the REHVA guidance. So version 4 is under development, and we hopefully can publish this during next week. And here you can see how infection risk probability will depend on occupancy time and on the room and indeed on the ventilation rate. So for small rooms occupied by a couple of persons, the risk is very high. It is very easily more than 5%. So, and indeed that's not acceptable. When in open plan offices, depending on the ventilation, we can see that we can stay below 5% for 8-hour occupancy if these are well ventilated according to current standards. So this is basically category 1 ventilation rate represented here. And we also can see that in the classrooms, infection probabilities are typically less than 5%, even in the wider ventilation range. So both the ventilation rate and room size will matter. And what is important, what is the resulting total airflow per infected person. And in these examples, it always has been 1 infected person in the room considered. So for just a comparison, there was very recent report by US CDS reporting that in home, if you share room with somebody infected, so very probably you will be also infected. And as ventilation in public buildings has much more capacity compared to the home ventilation, this is exactly so in that risk calculation. So even in well-ventilated apartments, risk is very high, and it is not easy to control. So basically in these buildings, focus should be based to the staircases and other common rooms, and in your apartment, it's your family, and then it is not so easy. One more fundamental issue is related to the filtration, how we can filtrate these viruses. And it is important to understand that the virus is not naked, so it is not 100 nanometer size what we need to filtrate. Expelled droplets are in quite a large size range, and they are larger than 1 micrometer. So the maximums having some couple of micrometers. And this means that really a common fine filters we are using for the outdoor air filtration are also effective for this virus filtration. Something what can be applied in air cleaners, so they don't need to have HEPA filter efficiency. Indeed, that would be perfect, but even lower efficiencies, if they provide high capacity air chains, that would be enough. Then it is perhaps a question how these air cleaners should be located in the rooms to to have effective air distribution, this is even more important, and indeed this capacity what is needed. And this is also an opportunity for more advanced personal protection devices, and such devices are already now available. Basically, the only thing you need to have a small fan and filter in your device, and indeed some battery to operate the fan. And then filtration is quite easy for such particles larger than 1 micrometer. Lidia told quite comprehensively about air currents. What I want to complement is, in this specific case, the main problem was the lack of a ventilation. Basically, this space was not ventilated. But indeed, low velocity air distribution and good mixing is something what is probably the most robust and is needed. So this really provides a new meaning for the air movement and air distribution. So to list the research needs for the general ventilation, it's quite a long story, but let's say this low velocity air distribution with good mixing for effective dilution, that's quite important when to organize the ventilation so that it will provide some local exhaust effect to remove virus-containing particles immediately. That's also very, very important. Then ventilation sizing and standardization. Today we can say that category 1 ventilation rates should be preferred, but perhaps even higher ventilation rates would be needed. And that's also a question for the future standardization. When somebody will go to start to use high capacity, demand-controlled, dedicated ventilation systems, what could be a solution, when this will provide indeed new challenges. So typically these systems operate in the range from 40% to 100% airflow rate, but if we will double the capacity, then we will need the operation range from 20 to 100% in order to maintain energy performance also in non-epidemic conditions. So this will mean new design for air handling units and also for the air distribution to work in much wider range than usually considered. When there are many ideas how general ventilation can be improved with targeted ventilation solutions. So many ideas how to deliver a small amount of a clean air because we need very little for breathing, basically. And there is a running REHVA occupant targeted ventilation task force led by Arsen Melikov and Risto Kosonen, where these questions are analyzed. Some of these can be very simple. You only need a fan in some most simple cases to generate targeted ventilation solutions, which might have quite a significant impact. But indeed, when these will apply mostly for the cases where location of a person, so fixed seats and so on. Then indeed we have many applications where the seats are basically fixed. So take buses, public transport, trains, airplanes, and already 2013 such seat incorporated personal ventilation solutions was developed for airplanes. And this is something we would really need to control this virus, spread of this virus. But today nobody is using this solution. So many solutions already exist, and it is time to take these into the use. Then it is also a question how to visualize and how to monitor that we have enough ventilation. Lidia told that we need a lot of CO2 measurement to make it visible, but CO2 is not constant and depends on many issues, and also more dedicated monitoring systems evidently will be needed for future buildings. Hygiene of the ventilation components and cross-contamination aspects, these are important for the heat recovery, and recirculation is also a special concern. to be studied, what is the real effect and how these can be controlled. And some studies regarding to carry-over effects, for instance, in heat recovery, are very old, from 1980s. So should very much be repeated because there are new technical solutions, and we need to know how these specific virus containing particles will behave in these devices. So to conclude, there are indeed very many possibilities to improve ventilation solution to reduce the risk of infection diseases, especially in public buildings where we anyhow have a high capacity ventilation. What is needed already now, we can recommend to use a category 1 ventilation rates, but more significant improvements may be needed. So future research should tackle outdoor air ventilation capacity, air distribution, cross-contamination, air cleaning, and IAQ monitoring aspects as a first priority. And this is also something for the retrofit solutions, as this energy retrofit is very intensively ongoing. Would be very important to integrate these ventilation solutions to the retrofit. And indeed, this is a note for the research funding agencies, but we urgently need such a practical solutions. And finally, yes, it's very important also to update building codes, standards, and the guidelines, so to be ready for future epidemics. Thank you very much.
Thank you very much, Jarek, for your presentation. As we mentioned at the beginning, we took questions exceptionally after the presentation of Professor Morawska. But I propose that we keep going with the presentation, and our staff will take the questions, and we will have a session of discussion at the end of the session. So I propose to move directly to our next speaker. Our next speaker is Hywel Davies. Hywel is the Technical Director of CIBSE. CIBSE is the Chartered Institution of Building Service Engineers in UK. Since 2007, he leads the technical and policy development of this institution. He's involved in various aspects of policy, legislation, building regulation, and more recently he has coordinated the institution's response to the SARS-CoV-2 pandemic, and in particular the work on ventilation. So Dr. Hywel Davies, the floor is yours. And of course, Dr. Hywel Davies is also representing CIBSE in REHVA. So please, the floor is yours.
Thank you very much, Frank. I'm just having a little bit of a problem getting my screen to come up the right size. And good morning to everybody in Europe, and good day to those in Australia as well. I'm going to give a little bit of a change of focus now, in that everybody else has been talking about ventilation, and I want to talk a little bit more about the buildings as a whole. I really want to pick up on a comment that Lidia made in her presentation, that we do need to look at buildings as complete systems. And so I'm going to talk about some of the work we've been doing on safe reoccupation and use of buildings over the past few months. CIBSE was asked to produce guidance quite early on by the UK's health and safety regulator and others, and that's what's underpinned a lot of what I'm going to talk about today. So I think it's fair to say that in most legal jurisdictions, there's a legal responsibility under health and safety law for people to secure workplace safety. And workplaces doesn't just mean offices and factories, it means anywhere where people are employed. And the management of the building owner are the people who are responsible for safe opening. It's not something that they can delegate to the facilities manager or to engineers. It's an overall management responsibility, and in multi-tenanted buildings, every tenant organisation has a part to play in exercising that responsibility. Ideally, there should be an identified building safety manager who all of the tenants and occupiers of the building know and can talk to if they need to. So we've got a number of buildings which may now have been largely unoccupied for quite a time. And in every case, before we reoccupy buildings, there needs to be a risk assessment. And again, buildings are complete systems, and ventilation is very important, but there will also be gas systems and gas appliances in many buildings, and there are almost always statutory requirements to inspect and check those. We need to be mindful of water systems, which is another area where REHVA and CIBSE and others have done a lot of work over the years. Certainly in the UK, there are quite strict rules about checking for the risks of Legionella, and I don't think that we are unique in that. Electrical systems need to be checked. There may well be refrigerant systems containing F-gases, and I understand that there is no research to suggest that coronavirus in any way mitigates F-gas leaks, so they need to be checked regularly. And of course, lifts and escalators, there's quite a stringent regime for safety checks on them, certainly in Europe and in other jurisdictions. And again, those checks need to be undertaken and maintenance kept up to date. So these are all things that need to be thought about. And if access to buildings has been difficult, there may be some work that is needed to bring all of those checks up to date. But those things really need to be done before people are using those systems again. So other parts of the risk assessment that need to be considered: who's occupying the building? And by who's occupying, what sort of people? If it's being occupied by older people, there may need to be some consideration in the current circumstances because of what we know about the vulnerability to infection and how that increases with age. We need to know about how many people are in the building and what are they doing. If you've got a number of people who are largely sitting quietly doing desk work, that will be a different situation to one where you may have people moving around and possibly talking loudly. And from the previous talks, I'm sure you'll appreciate the differences between them. What are the hours of occupation? How long is the building occupied? And again, length of occupation and exposure has been picked up in previous presentations. When do people arrive? Do they all arrive at a similar time? And does that need to be managed? And how do people move around the building? Do they use lifts? Do they use escalators? Do they use stairs? All of these things need some thought. And I've already touched on thinking about whether any of these activities might lead to increased aerosol or droplet emission. Is it a building that's open to the public, or is it only for those who work for the occupying organisation or organisations? So there are a lot of things for building operators to address, and particularly around occupancy levels and hours. How do you make sure that people are maintaining social distancing within the workplace? How do we try to reduce the amount of traffic, particularly through entrance areas at the beginning and end of the day? Do we allow people to operate flexible working hours, or we have some people coming in early and another group who come in a bit later? All of these things need thinking through, as do welfare facilities and cleaning regimes. And it's important that staff feel confident that all of these things are being addressed. It's important that we think about the users. I know it's easy to think that it would be so much easier to be the facilities manager in an office if we didn't have to manage it with all of the office workers who come in and don't do things the way we want them to. And I can see Frank smiling, and I hope you can see my point. The reality is we manage buildings for people who occupy them, and the response needs to take account of user behaviour. And that means explaining what we're doing so that the users understand. If they don't understand, how can they operate the building the way we want them to? If we don't tell them, then actually it's our fault when things go wrong, not theirs. And if we don't engage with the users and take their feedback, then there's liable to be a lack of confidence in what we're doing. If the users feel that they have an opportunity to say, would it be better if we did this instead of that, then they will be more engaged, they will be more comfortable in the building, and they are far more likely to work with the operational regime that we're operating. We also need to think about the different locations within a building and what's going on in them, how long are they occupied for. I'm less concerned about a storeroom that somebody goes into for 2 minutes and leaves and nobody else goes in there for several hours than I am about an office with several people in it all day. Lydia talked about the need to balance different things, and the really big issue, particularly as we come into winter, is how we balance the need for more outside air and better ventilation with the need for people not to feel cold. And this is really important because if people feel cold, they're likely to intervene, reduce the ventilation rates, and increase the risk of transmission. So in any plan to reopen or occupy buildings at the moment, the balance between providing good ventilation and avoiding thermal discomfort is really important. And how can we operate our ventilation system to achieve a reasonable balance between people feeling thermal comfort and being well ventilated? And all of those things are going to need to be considered by the building manager. Really important that we think about common spaces, and by common spaces I mean entrance and exit areas, corridors, staircases, lifts, anywhere where a number of people may congregate and pass through and potentially touch things. These need to be thought through. Some buildings, it may be appropriate to think about having some form of visitor screening, maybe taking temperatures. There may need to be some thought about how lift control programs operate in order to support reduced occupancy of lift cars to maintain a degree of distancing. And we may need to look very hard at how we manage our meeting areas so that we restrict the numbers and as far as possible we avoid people. Meeting group one of half a dozen people go in and they all move the furniture around and they don't put it back at the end, and then meeting group two go in and they're then expected to touch all the same furniture. We want to avoid that kind of scenario, and again there may need to be enhanced cleaning for our meeting rooms. Maintenance is really important. I talked at the beginning about some of the statutory requirements. It's also important that routine maintenance is carried on, and that we make good precautions there for our maintenance staff. I'm not going to dwell on this. It's in the slide pack for those who want to look at it, but it's important that we maintain ventilation and that we're doing everything we can to dilute any material that does get into the airspace. It's important, and perhaps it's timely, that we remind ourselves of the other side of the Atlantic Ocean. With this pandemic, we're dealing with a lot of unknown unknowns, and we need both to recognise that and to be prepared to communicate it. There are a number of things about coronavirus that we just don't know. And because of those unknowns, we have to adapt the way we do things. We're not dealing with traditional source control where we know who is infected and where they are. We don't know who's infected and they're moving around, and they may be doing things that we're not anticipating. So we have to take a much more precautionary approach, and that's one reason for suggesting that we need higher levels of ventilation as far as possible. Again, that's been covered in some detail already, so I'm not going to dwell on it too much, but the guidance is in the slides for those who want to come back later. Really important that we target poorly ventilated spaces because, as Lydia's slide showed earlier, there is a law of diminishing returns here, and we really need to focus on the most significant. There's a real role for engineers here, and again, I'm not going to dwell on it because I think it's already been made clear, but we have a key role to play in helping the recovery from the pandemic. So, in summary, all buildings need a risk assessment. There are a number of things that we need to be looking at carefully, and this slide summarises them. And it's important that we don't only focus on ventilation, but the hand washing and social distancing is also really important. And as I said earlier, clear communication is vital. So there is some further guidance available, and it's listed on the slide. And with that, I'm going to say thank you very much for listening, and hand you back to Frank. Thank you.
Thank you very much, Dr. Davies. It was very also important to tackle this point, especially in this time where we're entering in some part of Europe in the second lockdown, and we have to think about what will happen next, and how are we going to reopen again the different buildings, especially after this winter period, where things are different according. If we want to look at what we have done for reopening in spring, it's quite different. So thank you again, Dr. Davies, and I will shift to the next speaker. Our next speaker is Atze Boerstra. Atze is Vice-president of REHVA, is a board member. He is currently working as managing director of BBA Binnen which is a consultancy company specialized in outdoor climate, based in The Hague in the Netherlands. He and his colleagues are involved in research in the field of mechanical engineer, architectural engineer, environmental engineering, and also, of course, indoor air quality and indoor environmental quality. Atze has a building science doctor's degree from Queensland University of Technology, and he also holds a master's degree from Delft University. He is an active member and a firm member also of GVVL, the Dutch HVAC Association, where he was tasked with knowledge dissemination, and he is a very active member of the COVID-19 REHVA task force and the cooperation with Professor Lidia Morawska and other researchers around the world. Dear Atze, please, the floor is yours.
Yes, thank you very much, Frank. I think you see my slides now?
Yes.
Yes. I anticipated that the rest would say quite a bit about the background of, if you talk about COVID-19 and the role that ventilation and air filtration, for example, can play. So I decided in my presentation to focus a little bit on practical solutions. And I'm doing this as my day job is IEQ consultant. So we come in a lot of buildings, and the last couple of months we've had a lot of clients who asked, can you please check our ventilation system? Are we safe enough? Or can you help understand why we had an outbreak a couple of months ago? So just some practical information that I would like to share with you. Before I do that, I would just like to point out that the thing we're talking about is not totally new. You can go back to the Romans even, but in history you see several people that already looked at infectious diseases and how they are transmitted. And quite a few of them, including, for example, Florence Nightingale, they pointed out already a long time ago that it's not just a matter of not washing your hands in time, but it's also important to look at engineering tools like drainage, ventilation, to make sure there's pure air in buildings, and to have good water. So it's not something totally new, and of course it depends on disease. One disease is more airborne than the other, but anyhow. Fast forward to 2020, one of the studies that really triggered me in my thinking about COVID-19 being a disease that in certain situations is transmitted through the air, past the 1 or 2 meter limit, was this study. This is a study from China. A couple of Buddhists, they went to an event somewhere. They went there in 2 buses. One group was in one bus and the other group in another bus, and they were sitting in the same place on the way there and the way back. During the event, apparently there were no people infecting other people, but we found out, actually the author of this paper found out that the people that were on specific bus, on bus A, they were actually infected by one person, see the Red Cross. And one of the things you see here is that this was only a 50-minute ride. It's 50 minutes to go there and 50 minutes to go back. And even people sitting away as far as 10 meters away from this infected person got infected, while at the same time, people sitting right next to it were not all infected. So this really tells you, these kind of studies, that in some situations, it's not about hand washing, it's not about keeping distance, it has something to do with the air, with ventilation. And in this specific case, they found out that the bus driver, because it was very cold outside, had put the system on recirculation mode a substantial amount of time. So an important study. Have a look at it if you have a chance. Of course, these kind of studies have led to new policies. For example, already before summer, we had the European Centre for Disease Control and Prevention that said things like this, like make sure your air exchange rate is in order, decrease recirculation, etc. I'd also like to point out that Angela Merkel already, since a couple of, maybe 2 months already, even on TV, is telling the Germans to not just wash their hands, but also to put a Schwerpunkt on Luftung, so to take care of ventilation in all kinds of situations. And you see this happening. I got some news yesterday from Canada, from Switzerland. You see more and more countries that now start to recognize the importance of having well-functioning HVAC systems and good ventilation, and maybe in some instances well-functioning air filtration systems. Well, then, if you jump forward to what can you do to make sure that these general recommendations by politicians are translated and are translated into engineering preventive measures. Of course, you can go to websites like the REHVA website, where you can find all kinds of suggestions. As Jarek said already, we will have sometime next week. We'll have a new version of the COVID guidance. I think many of you have seen it. If you didn't, please go there. Just Google on REHVA COVID-19 guidance, and you'll find the latest version. I'm not going to go through all of it, but it's partly about use of operable windows, partly about toilet ventilation, partly about heat exchangers, for example. And please have a look at the text, or wait till next week, because then you have a new version, and keep an eye on this. It's quite specific. Actually, the changes we do now, it's not super radical, but some things are clarified, and there are some minor changes in the new version. Then, like I said, I've had a chance to learn from some recent outbreaks here in the Netherlands. This was a relatively small one. This is a startup company somewhere in the western part of the Netherlands, where in March, one person went to a skiing trip, came back infected. He found out afterwards with his colleague. I mean, they're working partly in a big industrial hall and partly all together in one office room. And within a few days, 8 colleagues also got infected in this specific case. And they asked me, well, it might have had something to do with hand washing, standing close to each other, but maybe also ventilation was an issue. Can you have a look at it? What you see here in this specific case is they did not have mechanical ventilation. They had natural air supply through these kind of ventilation grills above windows, so Dauerluftung. They did not have substantial mechanical exhaust, just a little bit in the industrial hall, nothing in the toilet. So in terms of ventilation, it's not the best building. And when I walked around, I noticed that a lot of these ventilation grills were still closed. So actually, I opened them, I did some measurements, and I found out that if you open them, giving average wind speeds in the Netherlands, you have a ventilation rate of about 2. But if you close them, my estimate is that it's maybe even 0.2, but definitely not more than 0.5 in a winter situation. And of course, they did this because of drought problems. And I did some calculations and found out that, especially in the winter situation, the March situation, you can have pretty high CO2 concentration in a room, close to 2000 ppm. And actually, if you calculate this for like an 8-hour day, then you come towards like 50% chance of infection risk if you use the Well-Riley equation. So I basically told them the fact that you infected each other is actually in line with theory. And of course, I told them next winter, make sure you keep on ventilation and just put on a sweater because you need fresh air when you sit in a large room like this altogether. Then just 3 examples of some recent projects that I've been involved in recently. And in this case, the question was not they didn't have an outbreak, but the question was we want to make sure we won't have outbreaks in the future. So please check our ventilation system and other things, and tell us what to change to make our spaces safe enough. Which you can discuss about what that means. Here's an example of a consultation room in the city hall. So people working at the city hall, they go in this room, they have meetings with the citizens, sometimes 15 minutes, sometimes 1 hour or even more. And it's so then you talk about 2-person use. They put in some plastic shielding just to keep the light travelers from going from one side to the other. It's actually a little bit open here below. It's difficult to see in the picture. You see that it's ventilated with just this one device here in the ceiling. This is a little bit clunky, of course, to put the plastic thing just below this. But anyhow, so the question here was, are we ventilating enough? And it's an internal room, so no operable windows, and so they're totally dependent upon this issue. I basically told them if it's just 10-15 minutes, it's probably not an issue. But then they said, well, quite often it's like an hour or maybe even 1.5 hours. So please tell us if that is risky or not. Very small room. Like Jarek said already, the small rooms are more tricky often than larger rooms. In this case, we measured the fresh air supply. The total was 14, so that's 7 cubic meter per hour per person. That's not too much, like maybe 1.5 liter per second per person. In the Dutch building code, it says you should ventilate at least 14, a little bit more than 40 cubic meter per hour per person. I personally think this is not high enough. It's better to go for maybe double that. But anyhow, so this is much lower than what it says in the building code and much lower than what you would normally like. Like I said, it should be maybe 30 or 40 cubic meter per hour. The challenge here, of course, there's lots of talking. We know if you talk a lot, you spread more viruses. So that makes the situation even more tricky. We did some calculations here in terms of those Riley infection risk. This is just indicative calculations, but we found infection risk levels over 50%. Of course, this has directly to do with the fact that they ventilate very, very little here. We basically told them, stop using these rooms. They had other rooms actually in the building that were suitable too, where the mechanical air supply was much higher, and there had operable windows so people could ventilate between meetings. So, and we also told them to select maybe a little bit larger rooms for this. And actually, this is easy because most office workers were still working at home, so it was easy to find other rooms. Then a second example. This is a very interesting one. This is a classroom in somewhere in the Amsterdam area, and a school. Secondary school, no operable windows. Most schools in the Netherlands have operable windows, but not this one. They had a very old, induction system, like facade integrated induction system. You can see already on the pictures some of the nozzles even are crooked. We have other pictures actually where some were even broken. And in this case, they had lessons of about 80 to 160 minutes, and they had longer breaks than normal, I think 20 minutes or so, just to make sure that the mechanical system was kind of cleaning the air before new groups came in. But already we kind of told them beforehand, we're not sure that you're doing a good enough job here because you have a quite outdated system. Again, we did some measurements. Also here we found fresh air supply rates around like 10 cubic meter per hour per person. We have a specific code for schools, like it's called the healthy school requirements. There we say at least ventilate 20 cubic meter per a little bit more per person, per student. And again, ideally, I would like to go even a little bit higher. And of course, they are like a factor 3 lower, 2 to 3 lower than that. So and normally then you would say, okay, just use your operable windows a little bit more often, maybe every half hour, open them for 5 minutes. But in this case, they didn't have operable windows, so it was bad news. The good news is that they moved to a new building from January 1st. So, and the new building we checked, and it actually is very good. So it has very high fresh air, mechanical supply, and good operable windows, easy to use, and not so much noise from outside, so the windows can be used too. So from January, they're I think safe. And we told them, well, if you want to be ultra safe till Christmas, just put some portable air cleaners in all the classrooms, because they should be of the right type that we know of, filters out fires, like HEPA or with electrostatic filters. Okay, the last example I'm giving is from a living room in a nursing home. This actually is a nursing home where they had outbreaks before, so they thought during the second wave we just want to make sure that it's safe, or at least safe enough. Very tricky, because in nursing homes people complain about draft very easily, so to ventilate enough, whether it's mechanical or natural, it's super challenging in a nursing home. And like in other countries, we've had a lot of infections in nursing homes, so it's a big problem there, I think. In this specific case, they had a system that is indicated here on the left. This picture is actually not of the real nursing home I looked at. This is a very complicated system, so I won't go in all the details, but it's a combination of a fan unit that can heat and cool the air and actually uses recirculating air, partly a little bit outside air, and a unit. You can also buy these two separately. That is facade integrated, takes out outdoor air. There's a ventilator in here and draws it in. Actually, part of it goes directly in, and some outdoor air, like room air, actually goes outside. And there's a heat exchanger even here. Of course, you can ask if outside there's not like unwanted recirculation, but anyway, so it's a little bit tricky system, but it could work. The only thing was, in this case, they had in demand control setting, actually in eco mode they call it. So it was all about, it was programmed in terms of energy savings, and a lot of the time we saw the system was just not on. If you're only one or two persons, there could be half an hour or longer where the system is just not on. And this is not ideal during times of pandemics. Facility manager thought these are very risky system because it makes air to move around. And we told them, well, the most risky thing here is that you don't ventilate, you don't move the air. So anyhow. Again, the most important problem here, and this is my last slide, was that ventilation system was off. And that the actual fresh air supply was much lower than what you would like in a nursing home. Again, for nursing homes, officially we use these numbers, a bit over 20 cubic meter per hour. Again, for susceptible roofs like here, I would like to have a little bit higher values, maybe 35 or 40. Anyhow, so our first advice was, okay, reprogram the units. So maybe set point is instead of, I don't know, 1100 or whatever it was, and make it 500, so as soon as the system detects that there are people in there, it becomes on. So you dilute the air as soon as people are in the room together. And also they had other rooms that were underventilated in this building. Make sure you put so-called CO2 traffic lights in some of the most tricky rooms, also for example the coffee rooms where the personnel meets each other. And make sure you start monitoring what your CO2 levels are, because you probably have other rooms than just the nursing rooms that have problems. Okay, these were some examples from practice, and I'll give back the floor to Frank. Thank you very much.
Thank you very much, Atze, for your presentation. As I said, please send your question on the chat, and our staff is collecting the questions in order to have this panel discussion at the end. So thank you again, and I will shift to the next speaker. Our next speaker is Tarja, and I will try to say it properly, Tarja Takki-Halttunen. Tarja is the co-owner and the vice chair of the board in the Halton Group. She also served in different executive roles in the group. And Tarja also founded Indorium and was the HVAC consultant at Econo. She's a board executive committee member in technology industry in Finland, and she is also a board member in the Confederation of Finnish Industry and also in 2 technology startup companies. Tarja has also worked for 6 years in the United States of America in different positions in the Halton Group. And we are very pleased to have Tarja here with us to explain and show the group Halton and the position of shifting in design is integrated in the thinking of this group. Tarja, the floor is yours.
Thank you very much, Frank. You can hear me?
Yes, very well.
Yes, good. this is, I wonder why I have this one box here, but let me try to take it. Okay, good. Yes, I want to start by thanking my colleagues, Drs. Kim Hagström and Andrei Livshak, and also Ms. Sarah Marcotulio of helping me to prepare this presentation. If you want to know more about Halton, you can go to our new Halton website, halton.com. I don't really have now time to go through anything about the company. However, we are, of course, really interested in this COVID-19 pandemic and how we could help with ventilation, this situation that is devastating in the whole world. So I divided the contents of this presentation into 6 parts, starting with the risk assessment and continuing with a little bit of the air distribution and the importance of that. Then a couple of words about air filtration, and then UVC and UVGI purification. Also, I wanted to emphasize the clean air delivery rate, which is really important. And then I will end the presentation with something about especially displacement ventilation. So this Wells-Riley model has been mentioned many times already in this webinar, and I don't probably need to go into detail of it, but as everybody knows, this is a very good model of predicting how the clean airflow really affects the infection risk. And what we actually did, we checked the Wells-Riley equation. We took 2 real-life situations, the other one being the Skagit Valley, the coral practice of like a super spreading event, and another one was a birthday party where there were 25 people for 2 hours, and one had COVID, and then 18 persons, 72% became ill after this party. So when we looked at the Wells-Riley model and used the basic dwelling ventilation rate, the Wells-Riley gave 75%, which is really close to what actually happened there. The same was with this coral practice. It brought the same kind of results. So the estimation of infection risk using this Wells-Riley model demonstrates a possibility that the infection risk could be explained even merely by airborne exposure. However, there are so much we don't know about this virus. Of course, we cannot rule out that there may have been, of course, close proximity and fomite exposure as well. And then some words about the air distribution. Even though Wells-Riley equation assumes that the conditions are perfectly mixed, that's never the case really in a real world, and that's why the air currents and the air distribution methods and the patterns are so important to understand. Also, we need to kind of play the locating of people in the space and also looking at the air currents simultaneously, so that we understand what really happens in the space. And suddenly this is very important because of this pandemic happening now. Air filtration. This is very interesting, has been kind of interesting also for me to learn a little bit more about air filtration here when putting together this presentation. Jarek mentioned here that this SARS-CoV-2 the virus particle is never naked, and that's maybe something we should discuss. I haven't really checked how often, how valid it is. I understand that often these small, very tiny particles do travel with the bigger particles and form so-called colony-forming units. However, we wanted to kind of take a look at the SARS-CoV-2 particle size and how it is caught by the fine filters. This new filter classification standard actually starts from 0.3 micron particle size, this EPM1, the smallest particle size class. So it doesn't even include the size of the SARS-CoV-2 particle. But when we look at this on this slide, you can see on the right-hand side, you can see the graph by Kowalski and Barnfleth showing the American standard filters. For example, the MERV 13 is pretty close to the F7 we use in Europe, and if we look at that graph, you can see that the 0.12 particle size, the entrapment efficiency is about 40%, which again this new standard doesn't indicate, because it starts with a 0.3 microns. If we want to be certain and to capture all the particles, high efficiency and ultra low particulate air filters are the ones that we should be really using. Of course, there is this pressure drop is much bigger with these filters. However, as we don't really know how the aerosols, well, what's the particle size distribution of the aerosols in this pandemic, HEPA is of course the #1 choice. And also it's significant to kind of understand that each HEPA filter is factory tested and each HEPA filter installation is also tested, so we know how they operate. Here we demonstrate an effect of a mobile HEPA air purifier on the left-hand side. It's the same room with the basic ventilation, but the left-hand side has this very efficient air purifier with 1,250 cubic meters per hour, and it takes 5 minutes in this demonstration to really clean the air in the room, whereas the room without the air purifier, it takes actually 35 minutes just with the basic room ventilation, 150 cubic meters per hour. So if you have an efficient air purifier that also has an ability to distribute the air from the unit so that it flushes the whole space, it really helps in with the basic ventilation, which is rarely enough in this kind of pandemic. So of course there are other filters. Electronic filters may be really effective also in capturing SARS-CoV-2, and then it is really important to consider filters with documented single pass filtration efficiency and reported clean air delivery rate that I will cover later a little bit. But then with these electric filters, the ozone generation is always a possibility, and therefore it's important to make sure that the room ventilation rate is high enough to keep the ozone level below the threshold value. UVC and UVGI purification, this is a hot topic nowadays, and what I want to say here is that UVC purification is based on, of course, inactivating microorganisms in air and surfaces, and when it's used on surfaces, the exposure time is easily long enough to really clean the surface. But then when we use it to a moving air, kind of airflow, we have to be very careful in selecting the irradiation intensity so that the short exposure time is sufficient enough to really kill the microbes in the air. Of course, UV does not remove the particles themselves, so the supplementary filter is always needed with these systems. When we then think about the UVGI, the ultraviolet germicidal irradiation, it's a certain wavelength of the UVC between 250 and 270, something like that, nanometers, and what it does, it inhibits the pathogen's ability to replicate. We have to, of course, utilize then safety measures if we use UVGI, avoid eyes and skin exposure, and also use very low ozone UVGI lamps or no ozone UVGI lamps. There was a statement by William Barntlett at an ASHRAE webinar that when the radiation is over 200 nanometers, the ozone is practically blocked. So that's kind of interesting finding. But if there's possibly is ozone generation, again, it has to be verified that the room air ventilation rate is high enough to keep it under the threshold, the ozone concentration under the threshold value. And then the clean air delivery rate is very important to understand when choosing the mobile air purifiers. It's actually not the device cleaning efficiency only that determines the effectiveness. It's also the airflow, how much air is moving through the device. And here on the lower hand side of the slide, there is a kind of a question about the two different devices, A having very high efficiency, almost 100% and running at 100 liters per second, and then the other device with the 85% efficiency running at 120 liters per second. Which device is more effective in protecting from airborne contaminants? And the answer is that they are actually virtually identical, so that kind of shows the importance of the airflow through the device. And then I like to say something about this, especially the displacement ventilation. It's suddenly this is displacement ventilation is again. It has been earlier. It's been gradually used, and it's for COVID-19 and for this kind of airborne infection, inhibiting the spreading of it. It seems to be probably the best possible solution, like Jarek was also mentioning. And in this example, we have a classroom on the left-hand side with displacement ventilation and right-hand side mixing ventilation. And what we investigated here was the CO2 distribution, which is a representative of distribution of exhale aerosols that are less than 1 micron in size. And as you can see on the left-hand side, the indoor air in the occupancy zone is cleaner with the displacement ventilation. So that's of course something that should be now thought very thoroughly when designing new buildings that are pandemic safer than the current buildings. As far as restaurants are concerned, they are of course they are in trouble economically, and you know, people don't go there, governments don't let people to use restaurants, and there are several ways of helping restaurants so that the diners can go there safely. And one possibility could be to have a displacement ventilation again, and then local exhaust from the above the table, so that the air is collected at the table. It can be either cleaned and returned to the space, or exhausted out, and that would help already a lot in keeping diners safer. Then we have this other example and this is an example by Dr. Livshak of a dining in hot and humid climates. Here in Nordics, we always usually kind of forget that what it is like in Singapore or so. And if we take the dining event outside, it's of course safer airborne contamination wise, but then it's so hot. So Andre has put together this kind of an example that we could use this displacement ventilation to cool just the dining area, and keep that way also the diners safer from the diseases, airborne diseases. My last slide is here, and this is some very interesting what Lidia said about displaying the occupants, what the IAQ, indoor air quality, is with traffic lights. And so this is an interesting company, Canadian company, Control Energy, that has developed a airborne virus detection device, and this could be something, and these kind of devices could be something that we could mitigate the risk of catching the virus. So this actually ends my presentation. Thank you so much.
Thank you very much, Tarja, for your presentation that gives an overview of potential solutions. Thanks a lot. So I will give the floor to Atze for the different questions that we could have to our speakers. As we already had the question with Lidia, so Atze, I think you got the question from the team.
Yes, yeah. Lots of questions, so apologies beforehand if your question is not addressed, but I'll do my best. I would say ladies first, so I'll start with a few questions to Tarja, if that's okay with you, Tarja. One is about, you talked about displacement ventilation, kind of indicating that in some situations it's the solution. One of the questions was, how about thermal comfort and energy performance, if you talk about displacement ventilation? Are there any penalties on that side?
Well, typically, traditionally, displacement ventilation has been used for higher spaces, and that's how the air stratifies so that it's exhausted also from above the space. And if we think about the thermal comfort, it's if we are able to position the devices so that there's no draft, thermal conditions should be really good. Energy-wise, if you have a higher space, you don't have to make sure that you only have to take care of the occupancy, zone, and it can be warmer up there where people are not. So energy-wise, I think there's no penalty. It's probably better that way.
Yeah. Okay, thank you. There were also questions about filters. And maybe this is probably a question to Jarek too, because in your presentation you indicated that using HEPA filters is the royal route. One of the persons who asked the question said, well, I've seen literature where they say that even a standard filter like F7 is already pretty good in catching viruses. So that's the first general question, maybe to both you and Jarek.
Yeah, may I start, and then Jarek can say what's really the scientifically right. But our kind of approach has been that we don't really know the distribution of the the particle sizes in this aerosol cloud. I asked about it from Professor Ville Vuorinen at Aalto University, who's a physicist and very, very knowledgeable about aerosols, and he said that probably we could start with kind of think that most of the aerosols are between 0.3 to 0.5 microns. But then again, I just wanted to say that, well, the SARS-CoV-2, we know it's 0.12 microns, and how can we be certain that it's not there as it is, naked? Maybe Jarek has more information about this.
Yes. So actually, Lidia Morawska has measured these size distributions, and when we speak what human being is exhaling, what is the size distribution of these droplets, and this is true that they are never naked and start perhaps from some 0.5 microns, and majority is more than 1, ranging 1 to 10 and even much more. So the question that basically F7 or F8 filters, yes, they can effectively used, but indeed cannot be used in hospital environment when you need 100% efficiency. But in public buildings, F7 or F8 will be good and effective solution for particle filtration, including these virus-containing particles. For the manufacturers, I fully understand, but to market the air cleaner having such a low efficiency as F7 filter might be challenging, because it looks so bad in performance data. But yes, in practice, it would be an effective solution.
Okay, thank you. One other question about filters is, how about if you have a recirculating system and you have a return filter, you catch viruses on your return filter. Sorry. You catch your return filters, can the virus survive on the material, and how big is the chance that it kind of gets released when you turn them on? Maybe this is a question to you first, Jarek.
Yes. So we have recommended that if recirculation cannot be switched to 100% outer air, then you need to improve return air filtering, and minimum improvement is F8 filter. So it's according to new classification EPM1 with 80% efficiency. So then most particles will be filtrated. And indeed, there can be a small boost when the system is turned on and off, but this is not very significant, and it's important that this filter efficiency is good enough in return air. And it means basically installation of a new filter, higher pressure drop, and so balancing of the system and so on. It's quite a significant improvement what is needed in practice.
May I tell something? Yeah, it's one possibility, of course, in this kind of situation is that we would use UVGI or UVC at the filter to kill the pathogens that have been trapped there. So that's one possibility.
Yeah. I have a question to Hywel. There was somebody who was noticing that I think CIBSE has done quite a lot of work in the area of elevators, lifts, and COVID, but also other measures to make elevators more safe. Can you say a little bit more about this, what the recommendations are? Because I know other countries are struggling with this issue too.
Okay, thank you, Atze. Yes, we do have some guidance, and if anybody would like to see the detail, it is on our website. And we do have quite a weighty piece of guidance on lifts. certainly in Europe, there's quite a bit in the lifts directive and the supporting standards that set out what people have to do. And in most countries, whether they're in the EU or not, I think the legislation is fairly thorough on this. The big issue in the pandemic is trying to reduce the risk of people being packed too closely into a lift. So there is a need to keep numbers down, encourage people to use the stairs where they can, which has some health benefits, and making sure that the risk of people transmitting through common touch areas is reduced, whether that's people carrying their own something that they can use to touch lift buttons with. So there's quite a lot people can do. It just needs a little bit more thought, and perhaps we've all got into habits of using lifts that we've just got to unlearn and rethink, and recognise that there is a risk there, and also building operators need to make sure that the lifts are reasonably well ventilated. It may be that they need resetting so that they return to the ground floor with the lifts open when they're not being used, for example, if it's possible to do that. So there's quite a lot to do. There's quite a lot of guidance there that people can go and look at afterwards, if that's helpful.
Okay, thank you. In the meantime, I saw somebody in the chat who said, well, if you use UVGI and on mechanical filters, it will actually damage the filter itself. So I'm not a specialist in this, and the person refers to new X-ray guidelines about this. Anybody wants to react to this comment?
I'll just make a quick comment, Atze, which is that I think there's a lot that UV could do, and there's a lot that we still don't know about it, and there's a lot of work needed, probably quite quickly, because it could be helpful.
Yes, thank you. Yeah, that's exactly how we see it too. More studies are needed, for sure. But it's very interesting. UVGI and UVC.
I think we have 2-3 minutes left. There was one question referring to personal ventilation. For example, the bus case that I showed from good personal ventilation, I think they mean like fresh air supply integrated in the chairs or something close to your breathing zone, like we have in some airplanes. Could that be a solution? Jarek, you want to say something about this?
Yes, but personal ventilation really could be a solution in many cases. So, I mean, you can improve a situation in offices or wherever when you add personal ventilation on the top of general ventilation. And when we speak about transportation, buses and seats and so on, when this personal ventilation is something what should be must. So in buildings it is more complicated, but both applications in transportation and also in public buildings. Okay. And perhaps there is now new market need for these personal ventilation solutions, because this is additional investment and they are somehow not so flexible as general ventilation and air conditioning solutions, but we are in new situation, and I really hope that these will be taken into use. And focus should be more to the particle filtration with these new personal ventilation solutions. No need to provide a thermal comfort or to clean air, just to remove these particles. This is also something what will make this easier to apply.
If I may add to that, I think like in the bus case, if you have personal ventilation, still the bus driver can forget to put the system on. So additionally to that, you should have intelligent systems that maybe notice it when CO2 goes too high, and then the system kind of overrules the bus driver, like in this case. That's one remark. And also personally, I think if you talk about personal ventilation, because a lot of nursing homes all over the world are not ventilated well. They're not like well ventilated like hospitals. So especially in nursing homes, I think it could be good if you have like some kind of flexible personal ventilation system, I don't know, exhaust flows to pillars, etc., to make them safer, especially during a pandemic, especially in the rooms where people are that are infected. So I think with personal ventilation in nursing rooms and temporary solutions, there's a big market opportunity too. Okay, looking at the time.
I think yes, we have to close the session. Yes. So thank you very much, Atze, for the moderation and thanks to all the speakers for their presentation that were very, very, very instructive. And I want to thank our 300 participants. It's really great. So I see that you were even more than 300 at certain time to listen to our speakers for this session. So great thanks to the speakers. Thank you for the audience. And I propose to reopen the next session. I think it's 11:30. The second session of our Brussels Summit that starts at 11:30 with our colleagues from the Commission and dedicated to deliver healthy building in the post-COVID-19 Europe in the coming years. And Lidia opened the floor with rethinking the design, rethinking the potential of the potential industry development. So I propose that for those who are interested, that we see each other again at 11:30. So great thanks again to all the speakers and the panelists, and speak to you very soon. Thank you. Goodbye.